All right, so this is what I was going to draw on the blackboard. All right, what is it? The starting point down at the bottom is a growing universe, but it hasn't grown very much yet. Can you see the colors? Are there colors on there? From where I'm standing, there's no color at all. The colors are fine. Okay, what's the color down at the bottom? Red? It should have been blue because it should have matched my previous color. That's the starting universe. It's starting to expand. Every time it expands, it doubles. Let's say over a certain period of time, it doubles. Whenever it doubles, I'll represent that by the universe growing into two pieces, but then because those pieces separate from each other, because they're growing, they separate from each other, they get too far from each other to communicate, and so I'll just represent that by the universe bifurcating. Now, it doesn't really bifurcate. This is what you would call an idealization or a simplification. The universe doubles, and then it doubles again, and it doubles again. What is the color coding? The color coding is exactly the colors of the bubbles that we started with in the previous slide. Different properties. Each one of these lines is a universe in which somebody could live. Maybe they could live. Maybe the properties are appropriate to live in. And it just keeps going on, growing and growing and growing. As it grows, it produces more little pockets, It's diverse. Different pieces are different than other pieces. And there's a probability distribution of some kind telling you how probable it is as you move up that you're in a red universe or a blue universe or a green universe. These different colors could just stand for whatever different properties you like, whatever they happen to stand for. Different properties, and notice that there are places where the colors change. Those are these Coleman-DeLucia processes which boil off bubbles of a different type. That's that is very much like what an inflating universe looks like if we take into account that these bubbles can happen, that the Coleman-DeLucia bubbles can happen. Looks pretty much like that. That's a fairly good guide to it. All right. Let's imagine, here is where I was going to write some equations. Let me write the equations. Okay. You could ask the question, what's the number? What's the mean number, the average number of lines, bubbles, universes, whatever you want to call them, of a given color at a given time as you move up? Time moving up comes in discrete steps, the bottom, the next layer, the next layer, and the next layer. And you could ask, tell me if you can't see this and I'll make it bigger. What is the average number? Can that be seen? Yes? Good. What's the average number of universes or bubbles of type M? M could stand for red, blue, green, whatever it stands for. At time t plus 1, what's the average number at time t plus 1? In other words, when you go up a level of bubbles of type M, and that is equal to the average number of bubbles at time t twice the average number at time t. Why twice? Because it doubles at every stage. At every stage it doubles, so there's a source of new things. The source of new things is this doubling. That's the first term. Now, you lose some lines of type M. A blue line can turn into a red line. So you lose some, so you have to subtract. And what you have to subtract is a certain number, which is called gamma, and it's the probability that a universe of type M will spit off a bubble of type N times the probability or times the number of things of type M. This is summed over N. Don't worry if you don't know. I'll explain what this is, but just for the experts in the audience, and there are experts in the audience on these kind of equations, I'm going to write the equations and then I'm going to tell you what they mean. All right? And then there's another term which increases. This is loss. Things of type M become things of type N. So you lose things of type M. Right? But you also gain things of type M if N becomes M. And that's N sub N. Also summed over N. That's an equation. It's got a name. It's called a Markov process. I wanted to show you a picture of Markov, who was a very, very famous Russian mathematician and was responsible for these kind of equations. I looked on the internet and I finally found a picture of Andrei Markov, and it turned out to be a Russian not a soccer player. You know, those guys who beat each other up with sticks. Hockey player, yeah. All right. I'll just tell you briefly. What this equation says is the number of each type at a given level is first of all the number that were there before that but doubled because each time it doubles, plus some loss because you lose some of that type when they become other types, plus a gain when other types become the type you're interested in. So it's a balance. It's a balance, a statistical balance. Anybody who knows this kind of equation knows how to solve it. And guess what you find when you solve it? You find that if you were to follow one of these tracks, branches, you are somebody who lives in this. You don't get to see the whole thing. All you get to do is follow along a line, a branch, leading to a branch and a branch. And these equations simply tell you what the probability is that you see different things as you move along the branches. Guess what it says? It gives exactly the same answer as Boltzmann's box. Exactly the same kind of answers, the wrong kind of answers, the kind of answers which say you come to a dead end of equilibriums and fluctuations, and this kind of universe, you lose again. You're back in Boltzmann's box. Even though it doesn't look anything like a simple static box. It doesn't look anything like it, and yet it comes back to exactly the same thing, the simple static box if you follow your way along there, and what you find is a universe dominated by fluctuation, where almost all of the time, if you saw something, it would not look like what you would expect to see because it grew out of fluctuation rather than the one-shot kind of. In other words, the point is, you keep going up and up. That doesn't terminate like that. It goes up and up and up and up and up and up. And if you keep following it up, you eventually just discover that there are recurrences, back and forth, Boltzmann's brains, normal universes, and you haven't won. You still have not understood why time is a one-way street that goes from something very simple to something complex, and that's it, end of story. You have not explained that. Well, I like to describe this by saying that it's led to a stagnant pool. It's led to a stagnant pool in which the only things that ever happen by random fluctuations. If a little vortex happens, it happens not because there's a flow of water, but because just by random accident some molecules might assemble themselves into a vortex. That vortex is very unlikely to look like the kind of vortex that you would get from a flow of water. The universe expanding out of the corner of the room is like a flow. This is like a dead end. So almost every theory we know of the universe either is empirically wrong or ends in this kind of dead end where the things that happen are just random fluctuations. However, remember I told you about the crunches. If there are cosmological constants which are negative, the universe can crunch. Well, that means these bubbles have the potential possibility of dying. This is very much like the tree of life, and the dead ends are like species which just die out to some extent. Red might correspond to the kind of universe that crunches. It ends. If it ends, it doesn't continue to branch, it doesn't continue to grow. You'll have to modify the equations. The modification of the equations involves one new term here. The one new term has to do with the probability of dying. And that just gives you a minus. Why? A minus because it removes probability. A constant, doesn't matter what it's called, gamma m times nm. Now don't worry about the equation. The main point is it changes the equation. And what does it change the equation to? Let me just look at these terms. This term is a kind of source. It's creating new things. This is a sink. It's eating up things. The equation has turned into an equation which is very, very similar to the equation which you would have if you had a source of fluid on one end and a sink down at the other end, so that the fluid flowed from left to right, from source to sink. Well, guess what happens when a fluid flows from source to sink? It creates eddies endlessly. It creates vortices endlessly. Those vortices, however, have a very definite sense of time. Time does run from left to right. Somebody living in one of those vortices would realize the vortex was born somewheres and would run out of steam somewheres. Very unlikely to see a vortex propagating in the opposite direction. A flow like this is exactly what you need to understand why time is a one-way street. The multiverse, the idea of a fractal flow, these equations here, appear to be possible to give you a universe which runs in one way. Now, is this going to run into trouble? Are people going to analyze it and discover again that it leads you back into Boltzmann's box? I don't know. But at the moment, this is the state of the art. This is as much as we know. I've taken you through all the various cosmological assumptions from Boltzmann's box to the fractal flow and told you what they have to say about the arrow of time. I don't think we're finished. This may or may not be the right answer. And if you invite me back with a blackboard in about 5 years from now, when I will be 78, I will try to tell you the answer. Thank you.